So we left off last class talking about special points on a graph, and the whole point of this was so that we'd be able to compare and contrast different graphs and functions. So today we're going to be talking about domain and range of a graph, and this is so that we can continue to compare different functions, types of functions throughout the rest of the year. So we've been talking about domain of a function and how this is the x values or the input of the function. And since we know that x values extend from left to right across a graph, when we're talking domain, we want to read the graph horizontally, as in look at the x values. Okay, so whenever we're talking domain, you always want to read from left to right across the graph. The reason that we're reading from left to right, it's sort of like the way we read a sentence from left to right, is because we want to extend from the most negative numbers. Think of this as a number line. Over here is the really negative x values. Okay, and if we continue to count up, we'll get to very positive x values. And a lot of times in domain, you're going to see numbers like positive infinity and negative infinity. So negative infinity refers to arrows pointing off to the left on your graph, pointing towards negative infinity, whereas arrows pointing off to the right are going towards positive infinity. And if you have a starting or a stopping point, you'll use those points also to talk about the domain of a function. So there's two different ways to talk about the domain of a function, to communicate it to your reader. One way is interval notation, and the other way is inequality notation, and we're going to be using both of those today. Alright, so if we read this graph, this first example, this linear function, from the left side of the graph to the right side of the graph, we can see that it goes on forever in both directions. So I mentioned before that you should always be reading your graph from left to right. So that means that we need to talk about the graph from left to right. Alright, so over here on the left-hand side, the graph is pointing towards negative infinity. Alright, so I'm just going to dive right in with interval notation. We start at negative infinity, and we go on forever to positive infinity. And we close our brackets. So interval notation is always going to be written as a starting point, a stopping point, and then surrounded by brackets. These brackets here, they look like parentheses. This sort of looks like an ordered pair. These are called soft brackets, and that means that we don't include these endpoints. And the reason we're not including the endpoints is because they go on forever. We sort of talked about last class how we can't really ever count to infinity. So anytime we've got infinities in interval notation, we're going to use these soft brackets. I'll show you an example of hard brackets in just a sec. So inequality notation is just another way of talking about domain, and you guys are well versed with inequality notation. There are two acceptable ways to write the inequality notation for this example of this function that goes on forever. One is just this kind of fancy looking R that has two vertical lines making it up that indicates to your reader all real numbers. So this fancy looking R here says all real numbers to your reader. Another acceptable way to write in inequality notation is negative infinity is less than x is less than infinity. Both of these are okay ways to talk about the domain of this function. Alright, so this second example, if you read this graph from left to right, tracing along the graph, you can see that there's no arrow heading towards the left side. So there's no arrow going towards negative infinity. There is an arrow, though, going towards positive infinity. Okay, so unlike this first example of this linear function, this one does not have a domain of all reals. This has a restricted domain. Alright, so we want to talk about this starting point here. And since we're talking domain, we want to talk about the x value of that starting point. Alright, so the ordered pair for that starting point is negative 5, 3. So if we're going to talk about the domain in interval notation, I want to talk about on the left-hand side that the graph starts at negative 5, and that from there it goes on forever to positive infinity on the right-hand side. So it's starting here at negative 5, and it's going on forever towards positive infinity. Now let's put some brackets on this. So I mentioned before that for these infinities over here, we used soft brackets, okay? And we always use soft brackets for infinity, so I can go ahead and put a soft bracket on this. For this negative 5, since there's an actual point here, I can touch -5, I'm going to use a hard bracket. So this bracket here is referred to as a hard bracket, and that means that it includes that point. All right, so if we want to write inequality notation of this domain, we would say x is greater than or equal to, because we have that closed point at -5, -5. So x is greater than or equal to -5. All right, so this next example, if we read our graph from left to right, we can see that there are arrows going towards the left, so going towards -infinity in terms of x values, and arrows going to the right. Okay, so this domain is, just like the first example, all reals. So if we want to write a domain of all real numbers in interval notation, we would write -infinity to +infinity. Again, soft brackets because we can't ever actually hit infinity. In inequality notation, it would be the same as the first example. So you'll often see it written as this fancy looking R, but another acceptable way to write it would be -infinity is less than x is less than infinity. All right, let's do a few more examples. So here's another example. It's sort of hard to actually even see this function, but it's right here. It's another linear function. It's a horizontal line. All right, so if we're talking domain, what's going on? If we read from left to right, we can see that there's an arrow on the left-hand side, and we can see that there's an arrow on the right-hand side. So we can see that the graph is going on forever. Okay, so if we're going to do interval notation, it would be -infinity to +infinity. And if we were going to do inequality notation, it would be this fancy R standing for all real numbers, sometimes called all reals. And another acceptable way to write it would be x included between infinities. Okay, now this next example is pretty funny looking, so just bear with me here. We're going to do the same routine where we trace across the graph from left to right. All right, so if I start on the left-hand side, I can see now my graph doesn't look like it's over here, but I see an arrow here. So that means I'm going on forever on to the left in the negative direction. Okay, so if I just want to dive right in and start writing interval notation, I can see that it goes to -infinity. So I can start there at -infinity. All right, so now let's look at the graph. We're tracing and we're good. We've got domain values. I can see domain values, but then look at what happens here. So it looks like I get very close to 2, but I never get to 2. And then on the other side, so look at this dotted line, on the other side, I get very close to 2, but I never actually hit 2. All right, so there is a domain restriction where we never hit 2, and we'll talk about what that dotted line is called in a little bit. So we've got a domain restriction at 2, so we should say it goes from -infinity to 2, and it stops. We don't have domain for just a minute, and then it picks back up on the other side of 2 and goes on in the positive direction to infinity. We can see that it goes on forever over here in the positive direction. All right, so if we want to write it as an inequality, we can write it as x is less than 2 or x is greater than 2. These are not two things that you can write. Either one of them, you need to write both of them separated by an or. Basically, this is saying x can be less than 2, that's all the stuff that's over here, and x can be greater than 2. All right, so our last example, we're still looking at domains, so we're going to trace the graph from left to right. So you guys can see me tracing over this graph. Now let's look specifically at the x values. So I've got an arrow going to the left, so I can see that I go all the way to -infinity. And then if I follow this line, it stops at x equals -2. So I'm thinking maybe there's a break in the domain because I've got this open point here, and you guys learned back in Algebra 1 that an open point means that it's not equal to it. Okay? But look at this. If I look at x equals -2 up here in it's the same x value, just a different y value, I have a closed point, which means that I still have a point at x equals -2. And then the graph goes on forever. So this one's a little bit funny looking But the domain is all real numbers. The domain goes from negative infinity to positive infinity. It seems like there's going to be a break in the action at x equals -2, but it picks right back up at x equals -2, just at a different spot in the range. Okay, so if we want to write the domain in inequality notation, we could write that fancy R for all real numbers. And then, don't need to write interval notation. It would be negative infinity is less than x is less than infinity. Again, this is just another acceptable way to write it.